exercise 6A is really about establishing some definitions for indices. Now, much of this you will have come across before, but in terms of formal definitions, there may be some new content here, and I'll then just finish off this exercise with a couple of important notes to make. So let's get started. With a basic definition for an expression involving an index. So any expression of the form a to the x is called a power, where a is called the base. It's really important. I'm not sure how much emphasis may have been given prior in maybe stage 5 to identifying aspects of terms, but you're going to hear me talk about the base, and if you aren't familiar with what aspect of a term the base actually is, then you're missing some important information. X is referred to as the index or the exponent. Now again, those two words, hopefully, if you haven't come across them before, or you may not have come across exponent, but you will now become familiar with it. Of course, there's nothing special about using A and X. I could have used B and Y, where B is the base, Y is the exponent. I could have used M to N, M is the base, N is the exponent or the index. As long as you're just familiar with the term base, power, exponent. Now, there are a few specific situations to be aware of the definition of, because that enables you to identify some important values. For example, if a power or the index is 0, then we have a to the 0. You can replace that. Your base, any base to a 0 power, can be replaced with the number 1. And that's by definition. When you've got a positive integer for your power that is greater than 1, any positive integer, any positive whole number that is greater than 1, then there's many ways that you can actually write that term. So if the base is a and the positive whole number is 3, a to the power 3 could be written as a times a times a. There's no reason why it couldn't be written as a times a squared, and you're probably also thinking, well, there's no reason why it couldn't be written as a squared times a, and you're quite right. If it is written in this format, a to the n is a times 1 less than n, which we refer to as n minus 1, then it's identified as the recursive definition. Just be aware of that. It's not really part of the syllabus to understand recursive. However, it will be used throughout the textbook. A third situation for powers you need to be aware of is not only when it's an integer, but any positive rational number. Remember, a rational number can be expressed as P on Q. So we've got our base to the P on Q power, can be defined in two ways. It means the qth root of a to the p, or the qth root of a separately all to the p. Now, there are times when you might want to write it in this format, and there are times you might want to write it in that format. And finally, when the power is a negative rational number, or it could be negative rational. Now, this seems to be the one that lots of students are not that familiar with for some reason. Maybe in stage 5 you didn't deal with a negative index very much. However, you will need to become familiar with it very quickly. So, by definition, a base to a negative index is 1 over that base to the positive index. If you can learn that, then it will be very much in your favour because you're going to come across it quite a lot. There are index laws, and I'm sure you've been using these, so I'm sure you'd be aware of them. If you add the indices, then it's come from the product of the same base and to given indices or given powers. It may be written now without the multiplication sign, but with a dot. Now, some students initially find that notation a little bit confusing because it looks like a full stop sign. Do not confuse it with a decimal point. A decimal point really should come, for example, like that. That's a decimal point. Whereas if I wanted 3 times 7, I would write it where the dot is, I guess, at the bottom of the 3 or on the line. It's not in the middle like this is the decimal format for a point, a dot, and this is the multiplication format. Likewise, you know that a to the x minus y comes from subtracting the indices or adding the negative index, and adding the negative index is the same as a to the x being multiplied by 1 over a to the y, a to the x being multiplied by 1 over a to the y, which would, yes, simplify to a to the x on a to the y. Now, moving from there to here is important, from here to here, and likewise reverse. All of movements in any of the directions is possible, and it's good if you can make that transition without any problem. When you've got an index raised to another index, then we multiply the indices. You can see I'm using the dot notation for multiplication there. That's really a to the x multiplied by n. You can see why we introduce this dot notation, because lowercase x multiplication sign often look the same, especially in typed script. In freehand script, it's when I'm writing freehand, I can make the distinguish with a lowercase x and make it more curled. But when I'm typing it, a lowercase x looks very much like a multiplication sign. Again, you see the dot being used for multiplication. And when we've got a product of terms here all being raised to a power, we can separate them. So it's a to the x times b to the x. And similarly with a fraction, you can separate out the fractions. And again, this seems to be a property that students are not all that familiar with. A over b to the x, almost all get a to the x, but often many miss b to the power x. And now for just something to be aware of. In a question that says simplify and clearly involves powers, they're very often set up in such a way that although there's a 9 here and an 81 there in this example, the bases could be the same. So we could be reducing both of these terms to the same base. Now you may wonder what's the advantage of the same base, but I'm sure you don't really. When you've got a to the x times a to the y, then you add the indices. So we need this. We need to have the same base before we can start adding the indices. So yeah, like I said, they're very often, the questions are often set up such that we can express these both to the same base. So you can see that 9 is 3 squared to the minus 3/4, and 8 is 3 to the power 4, all to the 2/3, which would give you 3 to the minus 6 on 4 times 3 to the 8 on 3, and we can now add the indices. So minus 6 on 4, add 8 on 3. I'll probably have to go to a calculator for that, which is 3 to the 7 on 6, and we could leave it like that. Also, just a reminder that negative numbers don't have a square root, not in this course. When you start extension 2, you'll see that you can take the square root of a negative, but not in this course. And so you can't take the 4th root, or in fact any even root of a negative number. However, you can take the odd root of a negative number. So negative 8 to the 1/3 makes sense. And we want the cube root of negative 8, and we know that's negative 2. Why does 0 to the minus x? Why is 0 to the minus x undefined? Well, if we use the definition of a negative power, it is equivalent to 1 over this to the positive power, but a fraction cannot have 0 in the denominator. Hence, 0 to the minus x is undefined. You should be right then to get started on 6a.